Hello everyone, my name is Resa, and thanks to previous presentation, now you're familiar with Brownian motion and the stochastic process. Let's go. A mucus protects epithelial cells from foreign particles, and we have mucus in different organs and tissues, and at the same time mucus is a barrier against the delivery. Mucus is composed of water, DNA, lipid, and mucins, which are mainly responsible for the viscoelastic properties of the mucus. Usually particles cannot transport and penetrate the mucus effectively, then they are discharged. There are two types of interactions between a nanoparticle and mucins, which is either a strict interaction or excluded volume effect, and on all other non-strict interactions like electrostatic, hydrophobic, hydrogen bond, etc. And we aim to understand the physics behind this process and how they affect each other. To model this process, we simply solve the equation of motion for each single particle. Here, MP is the mass of particle, V is particle velocity, T is time, FB is the Brownian force, which is a random force due to the collision with solvent molecule. The second term is direct force, and the last term is all other pairwise interactions between a particle and mucin, which can be either a strict repulsion or electrostatic interaction and H bond. For a strict repulsion, we use the famous Lennard-Jones potential. Here, epsilon is the base energy, P is the sum of particle and polymer diameters, and D and R is the distance between particle and polymer chain. And there is a cutoff value for this Lennard-Jones potential. We used a generic exponential function for electrostatic interaction. Here, UE is the extent of electrostatic interaction, and K is the interaction range, which is equivalent to the Debye length. And for H bond interaction, we use this potential, which has been successfully used by other researchers for modeling H bond interaction in their studies. Here, UH is the extent of H bond interaction. By solving these equations, we obtain the particle trajectories, then we calculate mean square displacement, and finally we obtain diffusion coefficient or diffusivity. Figure A shows the unit cell used in our simulation. Here, the edges shows the polymer chains, and B shows the average mesh size of the mucus, and we impose the periodic boundary conditions on all walls to approximate an infinite system. Figure B shows the sample particle trajectory over time, and the color bar shows the elapsed time. And figure C shows the distribution of the particles at the end of the simulation, and color bar shows the particle's velocity. First, we consider the pure solvent like water, and there is no polymer chains. So we use these parameters, T equal to 35, and this viscosity, and for different particle size, we obtain diffusivities and compare our model prediction with those of Stokes-Einstein relation, and a good agreement was obtained. And we call this diffusivity D naught, which is diffusivity in the pure solvent, which shows the amount of diffusivity hindrance due to the existence of polymer chains. Then we considered, and we added strict and electrostatic interactions, and we considered two cases. a strong electrostatic attraction and a strong electrostatic repulsion. As you can see, for the case of a strong attraction, the particles are trapped in the corners due to the presence, because the effect of three perpendicular polymer chains add up. However, when we have a strong electrostatic repulsion, particles tend to stay at the center to avoid any interaction with the polymer chains. And if we compare the obtained diffusivity, we see that when we have attractive electrostatic interaction, the diffusivity decreases so fast. However, for the case of repulsive electrostatic, we see that diffusivity decreases monotonically and slowly. And this plot shows that the absence of any electrostatic interaction is better than having either attractive or repulsive scenario. Then we introduced the H-bond interaction to our model, and we excluded the strict repulsion to focus between the interaction of electrostatic and H-bond. If we have electrostatic attraction and H-bond attraction, the results can be predicted easily, and that's not interesting. That's why we consider electrostatic repulsion and H-bond attraction. First, consider the case where UH is equal to 0, and you see that when we increase the strength of electrostatic repulsion, diffusivity decreases. However, when we added H-bond attraction with this strength, we see a non-monotonic behavior between diffusivity and UE. This results show that one factor can mitigate the effect of the other factor to raise the diffusivity. However, when we have when UE is too large, diffusivity decreases again and fall. Then we excluded electrostatic interaction and we considered a strict repulsion and H-bond. And similarly, we obtained a non-monotonic behavior here. And if you consider these two cases where UH is equal to 0 and there is only a strict repulsion, we see that this diffusivity saturates quickly, which stems from the presence of a cutoff value for Lennard-Jones potential. Interestingly, there is another crossover here for larger value of epsilon, and at the moment we don't have an explanation for that. Now you may wonder how these two interactions compare with H-bond attraction. To respond to such question, we consider three different cases: H-bond interaction alone, H-bond and strict repulsion, and H-bond plus electrostatic repulsion. And we varied the UH from 0 to -10. And you see that if we have only H-bond attraction, we obtain a lower diffusivity. However, when we add either a strict repulsion or electrostatic repulsion, diffusivity increases. But we see that the effect of strict repulsion is more dominant for larger UH values. However, the effect of electrostatic repulsion is more pronounced for a smaller UH value. This is because this stems from the used potentials, the used parameters, and the fact that this Lennard-Jones potential is highly nonlinear, and when we have a strong a strong H-bond, it can bring more particles to the range of Lennard-Jones potential. But this electrostatic repulsion has a longer range and can affect particles even when they are at the center of the unit cell. To summarize the obtained results, we showed that non-stick interaction play a key role on the transport of particles through mucus. And we found that the particle transport through mucus is charge asymmetric. And finally, we found that H-bond attraction can mitigate the effect of either steric or electrostatic interaction to raise diffusivity. I'd like to thank Mitex and NSERC for supporting our project, and please let me know if you have any questions.